Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be discussing addition reactions. So where we're thinking specifically about how an alkene like this one, which has a carbon-carbon double bond, reacts with a range of different substances which add to the double bond to get incorporated into that structure. So I'm going to be using some of these models to kind of illustrate things to you, or hopefully that helps you to see what's going on a little bit better. If I just move them to the side for a second here, so that we've got a little bit of space to write. So with an addition reaction, we're taking this double bond, we're breaking it apart, and then we're adding some other smaller molecule kind of into it. But so, in order for that to happen, what we need to do, there's kind of three steps that happen. So that the double carbon-carbon bond breaks. The next thing is that the covalent bond in the reactant, or the other substance, breaks. And lastly, then new covalent bonds form to the carbon atoms. Okay, so let's see if I'll see if I can keep those there and see if I'll try and work kind of in this space down here so you can see it. Okay, so if we've got this substance here. Okay, so which is ethylene or ethene. Okay, so the first thing is that one of the double bond, one of the bonds here breaks. Okay, so this bond is now broken. If I kind of can lay that down there a little bit for you, actually turn it around there, see if that helps. Okay, so now I'm going to add a hydrogen molecule into this structure, which is kind of the simplest sort of thing that we might go for. Okay, so then what happens is that this bond breaks. Okay, so in this kind of in this middle sort of step, we have only a single bond between these carbons. This covalent bond is broken, and this covalent bond is broken. And then what happens is that now this is where the addition is going to take place. This hydrogen atom is going to join onto here, and this hydrogen atom is going to join onto here. And so now what we have, now these bonds look different in the modelling at the moment, but they wouldn't actually in the real compound. We now have an alkane, which in this case has two carbons, so it's ethane. Okay, so in this situation that we have, by adding a hydrogen molecule into our ethene structure, we have formed ethane. So now I'm just going to, in this space, I'm going to draw out what that looks like with structural formulas. Okay, so it's like this hydrogen molecule has added onto or connected onto here. So perhaps it might have been better to even draw it kind of underneath there and show that this is where our new connections are made once these existing connections break. Okay, that's kind of the gist of what's going on here. But so just make sure that you capture that particular equation. Okay, so now I'm going to show you that it's not limited to just a hydrogen molecule. Okay, that lots of different things that we could be considering being added. And I'm going to go through these next two examples over here. Okay, but first I need to reset my ethene. Okay, so here I have my ethene, and now I'm going to add a water molecule. Okay, bump that up a little bit. Okay, so what I have, if I'm going to, might just even draw it up here as we're doing it. Okay, so I've got my ethylene or my ethene molecule here. Now I've got water. Now what's going to happen is that I'm going to draw my water molecule like this, because a hydrogen is going to add to one carbon and the OH group is going to add to the other carbon. Okay, so this is what I have at the moment. Okay, same as before. I break one of those bonds. I break one of these bonds. Okay, so now I have an OH and an H separate. I've got only a single bond in here and this connection here, and then I make the new connections. Okay, and so now what I've made is ethanol. Okay, and now this process needs an acid catalyst in order for this to happen. The exact mechanism is something that you don't need to know at this point, but it just has to do with how we can get the oxygen to connect on to that carbon successfully. And so now by addition of water, that we have made ethanol. All right, one more example. Okay, so now what I'm going to do is I'm going to be adding hydrogen chloride, HCl gas. Okay, so this is not hydrochloric acid where it's dissolved in water and has dissociated. This is as a neutral molecule. This is, yeah, so as a complete molecule. Let me just adjust my camera there a little bit there. Okay, so what's going to happen, just as before, we break one of these covalent bonds in the double bond. The bond between the hydrogen and the chlorine breaks, and then new covalent bonds form. And we produce chloroethane. Okay, now in this sort of situation, it's actually quite interesting because what we see is that we have more than one possibility, more than one way around that it could form. Now, in this particular case, it's probably not the best example, so I might see if I can see if I can show you another one. But the principle here, before I demonstrate that to you, is that this hydrogen chloride molecule could add on this way, could approach the double bond this way, or it could actually approach that way. And so what happens is that's going to influence which carbon these atoms connect to. Now, like I said, in this case, that doesn't actually really matter, but let's have a look at a situation where it does. So let's look at this. So this is propylene or propene. So what we have here, it's 3 carbons with a double bond between 2 of them, and then this methyl group that's hanging off the side. So some students would incorrectly name this as methyl ethene, but that's not technically correct because it's all part of the carbon chain. But so if I take my hydrogen chloride, and if I look at this, and so let's say I'm going to redraw this like this. So if I've got this, so in this one I can do it here, and it can connect onto here, and I'll show you how that goes. So here we go. I've made my substance here, trying to see if you can get the 3D kind of structure going on. Okay, and so it looks like this. Okay, so what I have here is that I now have 2-chloropropane. But the reality is that I've also got another possibility. Let me reset. So if I have my hydrogen chloride and it actually approaches this way instead, with the chlorine and the hydrogen oriented the 180 degrees, what then happens is that the chlorine's going to add on to here, and the hydrogen's going to add on to here. So that's going to give me a different result that looks like this. I'm not going to do the remodeling at this kind of stage because you've seen enough now to get the gist. Okay, so the chlorine's added on in a different spot. I now have 1-chloropropane. And so what we would see when we mix hydrogen chloride with this substance, with propene, that then we would get an equal mix of these 2 substances forming, because they're equally likely. Like the chance of the hydrogen chloride approaching from this direction is the same as approaching from that direction. So we would get a mixture of the 2 products. Now what we would see in real life chemistry is that depending on exactly what substance that we're adding, that there are other factors that will influence which way around it goes. It may not be a 50-50 chance. We might have a 75-25 chance or a 90-10. It all kind of, there are other factors at play that are beyond what we need to look at. Okay, but so what we've seen is that we've taken a double bond, and by breaking the double bond, we can add on a whole range of different substances. So it could be things like hydrogen chloride, it could be things like water, or hydrogen gas. For different processes, we need a catalyst to help facilitate the breaking of bonds, but otherwise then shows that one of the power of alkenes like this is that we can convert them into lots of different substances. All right, thanks very much for watching. Bye for now.